All right. So up until now, in the previous lecture and in the lecture before that, what we saw was some particular models, be it let's say parametric or non-parametric. So in parametric, we saw Gompertz, we saw McHam, and we saw a family of both of them together as well. And in non-parametric, we saw a Kaplan-Meier method, and the other method was Nelson-Allen method. I mean, these are the estimates that you can use to figure out the shape of your survival function, or let's say just to, in short, answer any question that you might have regarding the hazard function or the survival function for a particular population that you're looking at. But now sometimes what can also happen is, I mean, not every time in a population you are interested to know about the whole population. Sometimes you might just want to compare between two of the subsets of population. So let us say I divide my population into male and female, and I want to see what is the mortality rate um, for males and what is the mortality rate for females, and if at all they differ from each other or not. So there will be some significance testing that we can do over here to figure out if there is any particular difference between the mortality rate for males and the mortality rate for females. So this is one thing. But again, I think so the very nature of the population not being homogeneous every single time asks us to do something about it. Because whenever I use, let's say, Kaplan-Meier or Nelson-Allen, I'm kind of assuming some mortality rate. So I put some assumptions on the mortality rate, and I assume that these are true for the whole of the population. But this is not always true. So we can expect there to be some differences for this particular estimates for some subsets of the population. So one example I gave you guys now was about dividing the population between males and females. But you can also have more divides. Like let us say if you're looking at the effect of smoking on the mortality rate, then you can divide your population into males and females plus whether a particular person who is male or female smokes or does not smoke. So we will try to analyze what happens and how much of a difference there is between the mortality rates of, let's say, for example, a male who smokes and a female who smokes, or a male who smokes and a male who does not smoke. And once we figure that out, this will eventually help a particular insurance company to figure out the premiums that they should charge for each of these subsets of the population. So whenever we as a policyholder will go and will, let's say, take out some policy, there are some check boxes and there are some medical insurance things that we need to, I mean, let's say there is some basic health checkup that they'll ask you to do. And then on the basis of that information, they will try to figure out your mortality rate or whatever it is that concerns the insurance that you have carried out, and they will in a way determine the premium that they should ideally charge you. Um, and I mean, that will always be with respect to maximizing their profits. But again, keeping whatever it is that can happen to you and keeping their loss in check. So that's one thing. Okay, so when I'm talking about these males, females, smoker, non-smoker, I define these particular characteristics as covariates. So I think, yeah, I don't know how many of you have studied regression models as yet, but whenever I'm talking about covariates, these are nothing but the independent variables that I have on the other side. So I have some y here. Let us say, I mean, in the time series, you guys must have studied, right? Some alpha xt, or I mean, here, because I'm not considering time, I'm not gonna write a t subscript here, but what I might just write is alpha x1 plus, so alpha 1, alpha 2, x2, and so on. So let us say this, it represents my force of mortality. So I might say that this is the age of the guy. This represents the sex, whether the guy is male or female. So, and this will, so again, whenever I'm talking about the gender of a particular person, I know that I can either, so let us say if we are considering only the two genders, male and female, I cannot put my value of x2 as m and f. No, So what you will have to do is you'll have to assign some binary numbers. So I will just assume, sometimes let's assume that females are 0 and males are 1. So that if you have this particular x2, let's say 0, then it corresponds. So basically, if you do not have this particular term in your expression, then you will know that this is for a female candidate. And if you have, then you will see that yes, this is for a male candidate. So this x2 can take only two values, 1 and 0, depending on whether the person observed is male or female. And now, if you are looking at age, I know age is in number terms, so I can essentially just represent it as it is over there. And let us say we have one more down here. I'll just say plus alpha 3x3. So I can have something like, maybe smoking status. So let's say this x3 denotes smoking status. So I can have I can use 1 and 0 to denote whether a person is smoker or non-smoker. But sometimes I can also divide it in many more subcategories by saying whether a person is a chain smoker or just a smoker or, occasional smoker on so and so. So maybe I can just provide in a form a scale from 0 to 5 and ask people to categorize them on how much they're likely to smoke. So this particular X3 can take values from 0, 1, 2, 3, 4, 5, and so on. So again, these are in essence the three main kinds of covariates that we will look at. So one is where you are directly measuring stuff. So age here represents the continuous variable because you do not have to make any changes. Whatever the policyholder puts in as their age, that is what you might write here. But again, sometimes whenever we are talking about age, as we all know, there are three different categories in which we can classify a particular age that a policyholder will, say. And I think one of them is age last. So let's say if I am 23 years old and let's say if I'm 23 year and 4 months old, then I will only consider my age as 23. So that would be age last. And if I'm looking at, let's say, age nearest or age next, then these would be different. So if I'm, let's say, for example, looking at age next, then if at all I am more than 23 years old, let's say if I'm 23 years old and 4 months old, then I will consider myself as being 24-year aged, at least for the calculations and at least from the insurance company's perspective. So that age, I mean, that there can be certain categorizations in the age that you want to follow, but we'll look at that in much more depth in the next chapter. So in this chapter, we'll assume that age is just some continuous number. So it can take any particular number. And then the other thing we'll have is binary categorization for a particular covariate, which takes only two values. And that is why it's called binary, because 0 and 1. And the next is you can have a scale of observations where this might represent, some increase or a particular decrease in the thing that you want to categorize. So here, if you are looking at smoking status, then 5 might represent a chain smoker and 0 might represent someone who does not smoke at all. And in between will be the people who might smoke occasionally or frequently or something of that sort. So again, these are just the covariates, and I mean, this is just a normal definition of normal categories of covariates that we will observe. But again, this whole chapter, I mean, the name of the chapter itself is proportional hazard models. So why this name, right? So because we're studying models which are actually proportional. So I mean, so when I expand this particular model, or let's say if I'm writing the hazard function in this particular model, it is something like this. So let's say if I define this hazard function as lambda, and this is for ith individual. So I say that this hazard function depends not only on time anymore. So I think you can see time as the age, and you can see lambda as the mortality rate. So what I'm now trying to say is that the mortality rate does not only depend on age. It also depends whether you're a male or a female. It also depends on your smoking status and so on and so forth. So what I do is I classify my covariates. So I define my covariates as a row vector. So I denote them with a Z, and this is a 1 by P vector where I have P number of covariates. So for this particular example, I have one age, two sex, and third the smoking status. So I will have a 1 by 3 vector for this particular Z. So my Z will be something like age, sex, and smoking status. So if I say that I have a male, aged 5, and does not smoke, let us say 35, does not smoke. So I will represent this particular Z. So let us say I define my male I. So my ZI will be nothing but age 35 and male. So for males, I have denoted this particular thing as 1 and does not smoke. So 0. So this is how you will define your Z vector. So sometimes you might get confused whether this Z, if I write it as just a Z, whether this is just a number or a row vector. So sometimes you might put a bar over here or in the lower, in your coding, they haven't put a bar anywhere. And in this ACTED, they put a bar down, but I'm more used to putting a bar on the top if I'm talking about it. But again, this is just for your convenience, so it doesn't really matter much. So now what I'm saying here is that my hazard function for this particular I guy does not only depend on the time that I'm looking at, but also on the other covariates that I think might be helpful in determining the hazard function or the hazard rate for a particular guy. So when I'm talking about functional hazards model, the first term is proportion. The second term is something about hazard. Again, what I'm writing now will literally explain the meaning and the specification of this particular model types. So these are classified as lambda 0t times g of zi. So whenever I'm talking about lambda 0t, what I mean here is that this is some baseline hazard function that depends only on the duration, only on the time factor. And this is some another function which depends only on the covariates. So I've kind of separated these two kind of dependencies that I can have from a hazard function. So in the first, I have this, what I call as my baseline hazard function. So why baseline? Because whenever my value of these particular covariates is 0, this is the answer that I'm going to get. So we'll later on see what is this function g of zi. This is normally e raised to beta zi, and we'll see that. And if you see, if I put this as 0, e raised to 0 is going to give me 1. So what happens here at the end is, if let's say I'm looking at, a person who is female, then I know that this is my baseline because I've assigned them a number 0 here. So I won't have anything here. And if I'm looking at a non-smoker, I won't have any number here as well. So if you see in such a manner, you do not get any of these covariates in here. So in that kind of a model, you are only left with this particular term here, because everything that depended on the covariates is not there, because you're considering the baseline. So again, whenever I'm talking about baseline, when we study these models in depth, we will see that if I look at the non-parametric, or let's say, to be precise, the semi-parametric approach of figuring out this particular hazard rates dependency or something else, we'll see that this will not in a way help you to figure out the actual hazard function or the actual hazard rate or the actual force of mortality of a particular individual. Rather, this is much more useful to figure out the relativity. So the kind of questions that you will be much more able to answer better using this model is where your answer is in terms of proportion. So let us say if I'm looking at, how much of a mortality rate I mean, how much of a proportion, or let's say if I'm asking a simple question like, what is the proportion of the force of mortality for males who smoke and for males who do not smoke? So if you try to do that, then you will just see that this particular baseline hazard function. Can you guys see what I'm writing? I guess no. Hello, am I audible?
Yes, ma'am.
Um, did you guys understand when I was trying to explain this baseline hazard function? Or no? Because I have no idea when did I got cut off. Can you guys hear me? Hello?
Ma'am, can you explain this once again? Baseline hazard function.
Okay, so, okay, let me just start off again because, all right. So the very name for this particular type of models is proportional hazard models, right? So the very reason why it's proportional is because we can basically separate the effect of this particular two, which is one time, and second the covariates on the hazard function. So what I've done is I've created a baseline hazard function, which is denoted by lambda 0, and in bracket I only have t to show that this particular baseline hazard function depends only on the time and not on the covariates. And the other term that I have is g of zi, which is some function of the covariates. And again, I do not have t in bracket over there. So that in itself is independent of the time. So my g of zi will be same for a particular individual throughout all the times. And my lambda 0 t, which is the baseline hazard function, will differ for each time, but it will be same for all the individuals. So now if I were to plot this proportional hazard models, what happens is the graph that I see will always be in proportion with each another. So the reason, I mean, let us say, for example, you see some graph like this. Okay, so this is, let's say something, okay, maybe I should erase this. Let me just check the shape once. Okay, yeah. So, I mean, this is actual shape that a hazard model can take. And then it could be something like this. So what I have here on the x-axis is time. And if on the y-axis, I'm plotting the hazard rate for each of these respective times, what we have seen is for these two individuals, let's say this is for male, and let us say this, the downwards curve represents the hazard for the female. So what I am trying to say is that the proportion of these male's hazard and this female's hazard remains same throughout the time. So if you see the shape is kind of same for both of these. So if you see the actual value of the hazard is in a way determined by this lambda times this g, but there is a contribution of each of these separately to the way this graph looks about. So if I'm looking at this lambda 0 t, I know this changes with respect to t. So the very shape that it is here and then it decreases here is because of the baseline hazard function. And due to this g of zi, which is the difference between what the hazard rate will be for male and female, the final hazard rate, this difference is here. So the difference that you see in G of Zi for male and female will be observed here. So if you see, this is some proportion always. So this proportion always remains constant. But now you might question that the gap here is.
Ma'am, the screen is frozen.
Yeah, I guess so. Could you guys see the graph?
Yes, ma'am.
Okay, but now you cannot.
Yeah.
Okay, I think there's some internet issue. Well, it's back again. Yeah, can you guys see it now? Yeah. So what I was trying to say here is that this particular gap here, this represents the proportion. So now if you must wonder, the gap here is very large, but the gap here is very small. So that is because the proportion, I mean here the number, the hazard rate is also small. So for the same proportion, this particular female, the gap you see is also very small. But always remember that this proportion, so let's say if you do this male upon female, you will always get the same answer for each of the times that you're looking at. And because this proportion remains the same, is one of the reasons why you call this proportional hazards model. And why is this the same? Because of the very fact that you can separate the effect of time and the covariates on the final hazard function. So the stuff that depends on the time, we call that as baseline hazard function, because ideally we only expected our hazard function to depend on the age, right? But now we also see that there are some other covariates that matter. So this particular GZ item is the extra term that we have now added, and we see might be relevant to answering the questions about the actual mortality rate or the hazard rate if we are looking at. So again, I mean, you cannot always say that you will be able to categorize this hazard function in this manner, but sometimes this actually proves to be a very good model, and sometimes this will not. So you can also take this as g of zi comma t to say that this particular covariate function not only depends on the covariates but also on the time duration. But again, this is very complex, and we don't have these in the syllabus. So we'll only be restricting our analysis to the cases where I can devise these two functions, one that depends only on the time and the other that depends only on the covariate. Okay, so now even when we are looking at this proportional hazard model, there are two different methods we can have to estimate the hazard function. One is um, the parametric approach, where we will have a very, very strong assumption about the distribution function that we think this hazard belongs to. And in the other case, that will be bit, I mean, that can be non-parametric, but we have already seen that. And okay, so maybe if you want to figure out, or if you want to use the non-parametric methods for such kind of cases where we take covariates into account, what you can do is you can use Kaplan-Meier on these two subsets of population. So you divide your population, one part is male and the other part is female, and then you can use the Kaplan-Meier to devise the survival function for males. Similarly, you will analyze and devise and derive the survival function for females, and then you can compare and contrast and see what's going on over there. But sometimes all you need to know is not the precise proportion, but just how much of effect of age is on the force of mortality. So that, if you have a basic function, and then if you have, let's say, 3 or 4 customers, each some of them are male, some of them are female, then you can just plug in 0 and 1 and see what effect this particular person, female, is going to have on their force of mortality, which is what we need to care about. So in that cases, we will not care about the hazard function. We will ignore that hazard function. And if we do that kind of analysis, then that will be known as semi-parametric analysis, because again, you aren't indulging fully into analyzing all the parameters, but you are analyzing some parameters, which will be the coefficients of the function that you're going to have here for the covariates. So again, I have just said, I guess, a lot, but now let us first try to see what happens in the parametric model. So I'm just going to share the book here. Yeah, so if I'm talking about only parametric models, we have already seen, so some distributions we have already seen, some we haven't yet, and there are many more that you can use. So generally what happens is you will make an assumption. Sometimes if you make assumption that your hazard belongs to the exponential family, then you will get your hazard as a constant, which is the lambda here. So if you remember the TQX, which is the probability that this particular person will die by the time x plus t, given that he has survived up until age x, is nothing but f of x of the exponential model. And this turns out to be 1 minus e raised to minus lambda x. And we know this is the survival probability. So if you try to figure out the hazard rate, which is nothing but, I guess, f of x upon s of x, and this we have derived in the previous chapters, so I'm not going to do that again. So here, if you see, if I assume an exponential model, then my hazard rate stays constant. So no matter what time it is, my hazard rate will stay constant. And again, this corroborates the fact that my exponential distribution is memoryless. So it, in terms of hazard, it is trying to say that the probability of surviving for the next t years does not depend on how long you have already lived so far. But again, we know that this is not generally observed, but there will be circumstances that say if you are looking at, the random deaths which might happen due to something else, or let's say if you're looking at the heart attacks, then if a person dies because of anything other than heart attack, then you might want to use this. And here they have just again derived. So the next kind of parametric model that we can have is if we assume that my hazard function is viable, is from the viable family. So again, when I'm talking about viable distribution, you see the hazard function here is decreasing in nature as and when my time increases. But this is not the only thing that you can have in viable. So in viable, you can also have a increasing. So again, these will depend on what value your gamma variable take. So if your gamma variable is greater than 1, then this will be a monotonically increasing function. And if your gamma value is less than 1, this is what you will get. And I guess we all have already seen that if my gamma is just 1, then this becomes a special case of, then exponential becomes a special case of viable. So this constant hazard is just the exponential model, which is what we would have ideally expected, right? So again, these are, so again, not for every hazard you can use each of these models, but we'll have to see whether the thing that we want to consider follows a certain pattern, that if we assume a mortality or a hazard function to have this particular distribution. Okay, I guess I'm back. I don't know what's happening. I'm sharing the book. Okay, so I was saying that not every time each of these hazard function will be a very suitable approximation. But if you see that something is decreasing or something remains constant, then you know what kind of distribution you should assign to your hazard function. And again, here they have just proven for what case you have an increasing and a decreasing function for the viable case. And this is how the hazard function will look like in the case of the Gompertz mechanism. So here, what we assume is that, let us say if we are looking at Gompertz mechanism, so here you can just say that we are looking at the mechanism, because if your A is 0, then that will just become be Gompertz. So here, if you see that as the time increases, the hazard function is increasing at an increasing rate. So the model is actually remarkably a very close fit to model the adult mortality rate, as we have already seen, and much more so in actually developed countries than the other kind of countries. So again, this is the Mekin's law for the force of mortality. And you see we have two particular we have two particular terms here. One is A, which is independent of the age of this particular person. And the other term that we have depends on the age. So if you see, this age is in the power of some constant here, which is C. And that is one of the reasons why we call these as exponential hazard. So in exponential function, you have e raised to x. There is e is just some constant. So there is actually a very nice reason why we always use E and not 2, 3 or something else, which has a precise value which is known to us. So that's to do with the conversion in the basis. But yeah, all right. So the next model that we can also have is log logistic hazard. But again, these are not the only models that we can have. Any distribution that you can assume for your hazard function, that will become a fully parametric model because you've already assigned a particular distribution that you think your hazard function follows. So it could be log normal, it could be gamma with 2 parameters or 3 parameters or anything else, basically log normal. So here we have log logistic hazard. And you see this is a very interesting, this is a very interesting shape for a hazard function to take. So what it says is that as and when you increase the time, so if you are in the beginning, the hazard function increases, but then it reaches its peak and then it starts to decrease, and then it decreases to a very lower value. So as and when, so this might be, suitable to analysis to analyze diseases wherein if you survive after a particular point in time, then the probability that something will happen to you, which is hazard. So let's say if the probability that you will die is very less if you survive for some months. And basically this, again, depending on what you are trying to model, you can use each of these parametric distributions that we can assign to the hazard function. But again, whenever we're talking about these parametric models, we know that we are making a very strong assumption. When I'm saying that all of my data follows exponential, and that might actually hinder its application, and which is why we will study some another kind of models that is very generally used, and that is termed as Cox regression. So sometimes also known as Cox proportional hazards model, which is the semi-parametric one. But let us say, even before we do that, I just want to show you guys how this thing works with the parametric models. So now I know that I can assume any of these distributions for my parametric models. So let us say if I assume that my parametric model is Gompertz. So this is a very easy case because what I have is BCX. So let me just try to write something here. Okay, so now if I'm assuming that my lambda, so the part which depends on the t is the C raised to t. So again, t might represent age, t might represent duration and anything else. So this is what we have. And whenever we are looking at our parametric proportional hazard model, we can now say that these are the two parameters that we have. And this is the t, something that we expect depends on t. So this b, I can say, is my g of zi. And to be precise, I say that this is e raised to b times zi transpose. So if you guys remember, zi is a row vector. So what I'm doing is I'm just taking a dot product of this beta and this zit here. So what is this beta? To see what does this give you, first ignore what this is. And let us just go back to something that we studied. This was, right, this was what we took as an example. So if I want to rewrite this particular thing in terms of matrices, I can say that my y is equal to alpha 1, alpha 2, alpha 3, multiplied by x1, x2 and x3, right? So that if I multiply this row vector with this column vector, what I get is alpha x1 plus alpha 2 x2 plus alpha 3 x3, which is what I have here. So what I'm here doing is I'm just redefining this coefficient vector as beta. So again, I mean, I should have written beta 1, beta 2, beta 3, but just for the sake of having same notations, I'm writing this particular coefficient vector as beta here. So this is again a vector, which is, if you see, has one row. Okay, so whatever I wrote is gone. But what I was trying to say here is that we have some y, which will be beta times. So beta was what, one row then p, and I know that my zi is how I denote my covariate matrix. So this I take transpose, and this will become a p by 1. So I convert this row vector into a column vector so that this multiplication will make some sense. So now when I'm defining my, so again, I wrote that I'm defining my hazard function to take, let's call it again.